All right. Welcome, ladies and gentlemen. Thank you for joining us. We'd like to give a thank you to our sponsors for this track, NT Objectives, that have sponsored this room and this track. We've got a great talk for you now on using interactive static analysis for early detection of software vulnerabilities. And we've got Bill Chu and Jun Zhu from University of North Carolina, Charlotte. They're going to speak to you.
Thank you very much. The story we're going to tell, is essentially doing interactive static analysis as developers type. So people are used to using IDEs like Eclipse. When you type in, make a syntax error, you get warned of results, of errors. And we want to do that for static analysis, finding software vulnerabilities. That's essentially what we're trying to do. I think Michael Howard's talk this lunchtime sort of sets the stage very well. Education is a huge issue. People are not trained. And even if people are trained, they often forget because you have pressures, deadlines, etc. So what we're trying to do is to fill that gap, to be very mindful, to keep it at the front of people's consciousness. So the basic observation is current static and dynamic analysis tools are reactive. You sort of do this after you have reached some checkpoint, so you're not fixing the bug as you produce them. You're sort of some distance away from that, and they're typically run by security professionals. So our approach is, as I mentioned earlier, is really push the envelope of interactivity along with the construction of the code while developers are writing code. And therefore, by mixed initiative, we mean it's developer-oriented, and we want to keep developers in the loop. So the advantage is, it's proactive support of developers with vulnerability detection and prevention. We want to specifically leverage developers' knowledge about application context and logic to drive customized static analysis. Because a lot of times, when you use static analysis, you're used by security professionals, and they don't really have the application context. So we're trying to use this tool to bridge the two, and we'll show you a couple of demos about that. And of course, the whole idea is to drive to fix vulnerabilities as early as possible, because we heard Gene Kim's talk that sometimes you don't get around fixing these vulnerabilities, even if you know they exist. So there's two kinds of interactive static analysis we have implemented. One is interactive data flow analysis, which everybody is familiar with, the typical kinds of taint propagation and injection attack sort of analysis for detecting injection analysis, injection vulnerabilities. We also are experimenting with what we call interactive control flow analysis. The idea is sometimes you have security policies, invariants, things like access control policies, CSRF protection, etc., that you want to make sure that when you write code, you have satisfied those policies. And they're very difficult to detect with data flow analysis. They're really control flow problems. So we have some ideas on how to deal with that, and I'll share that with you. Now, I gave a version of this talk last year in Minneapolis at AppSecUSA. So I will spend the next few minutes, just sort of give you a little bit of a rehash of what we did last year, because some of you may not have been there. But we have done a lot of new work since then, so we'll show you more results, and we'll also show you some of our current research things that we're working on right now. So with that, what I'm going to show next is our prototype demo of a project called ASIDE, which stands for Application Security in an ID Environment. And part of this is an open source OWASP project, so you can Google OWASP ASIDE and you'll find the page. And so our design rationale is this is designed to be used by developers, not to security professionals. We want to have the developers be sort of recognize instead of recalling security problems. So instead of when I'm writing code thinking about what sort of problems I should prevent, we want the tool to tell the developers, hey, you want to think about that. All right? We want to, by minimizing extra burden on developers, and then we also want to, again, leverage developers' knowledge in terms of customized security analysis. So with that, June is going to show the live demo of our system, both the interactive data flow analysis and the data flow static analysis, and I'll come back and talk to you a little bit more about some of the theory underlying design issue behind it. So what he's going to do is going to show you an example in an Eclipse environment. So we have our plugin running, a side plugin running. So as you see that there are two warnings, and these warnings are generated because you are reading untrusted data. In this case, get parameter, right? So this is untrusted data. So if you comment it out the line, just show you how it's interactive it is. So if you comment it out the line, the warning goes away. If you uncommented it, it shows up. So this is the kind of interactive style that we're driving for. So now if you click on the devil's icon, it tells you that, in this case, you need to do input validation for this thing, right? And what we have done is we have put all the ISAPI library underneath, so, developer can go down this and choose what validation mechanism he or she wishes to choose. So if they choose something, say, for example, safe string, and then we'll actually generate code. Now, some developers don't like it. Some developers will like it. So this is, we're not saying this is one size fits all, but this is some of the options that you could do. In this case, the request parameter is passed through an integer, so you don't have to worry about it, right? So now you can also choose to ignore it, and this warning will go away. So the idea is, as you type in, this gets done. Yes, sir.
Where is the request to ignore that warning stored?
It's stored along with the workspace, along with the project.
So it's not in the code, it's in the metadata about the...
Right. Yes. Okay. Right. Now, we also do something with dynamic SQL statements. So if people ever were to use dynamic SQL statements, we warn them and say, this is not something you should do, okay? We want to stop them, in sort of very, very clear terms. All right, so this is just a very quick overview of what interactive data flow analysis looks like. So let's look at the next part, which is the interactive control flow analysis. And the idea we propose here is what we call interactive code annotation. So here's an example where, let's say you have accessed some sensitive database table. So the context is you have some security, application security people or security lead that for a project you would say, these tables are sensitive, okay? Whenever you change the state of these tables, you need to do access control or need to do protection of CSRF, right? And so what we do then, once you've declared that this is all policy-driven, you can write in rules, so it's not hardwired into the code. And as developers write code that touches these tables, we throw up a warning, right? We throw up a warning at the level of your entry-level method, whether it's an action or a servlet, something that starts your web transaction. So the reason we throw up that particular warning, you go back, that flag, is because in this procedure, in this function call, if we go drill into it, it actually accesses the database, right? So SQL statements. So our rule says if you touch this table, we want you to annotate for access control. So then you have the warning. So if you click on this flag, we ask you to show us where your access control logic is. Now, not every sort of piece of code passes as access control logic. They must be Boolean expressions. So in this particular case, you want to annotate, so you go back and you say, okay, here is checking the user session is not null. I annotate that. And then there's another one that the user actually owns the account, right? Now, so this information, again, is stored in the metadata that basically says, for this particular access control, these are actually my logic that does the access control check. Now, just to show you that if you just throw some, like assignment statement, you try to annotate that, you can add a third statement, and because it's not a Boolean expression, a site is going to just ignore it. So it's only looking for Boolean expressions that are connected along the execution path, so it understands the control flow path, all right? Now, the interesting idea, the proposal we have is, we also heard some speakers talk about code review being, this great idea of code review. But code review is incredibly difficult. One of the reasons it's incredibly difficult is because you got to talk to somebody, see what you actually did, right? So what we're trying to do is, doesn't solve all the problems, but the hypothesis is with a tool like this, you could start build some critical annotations so that somebody, without actually having to sit down face to face with a developer, I can pull up the code and say, for my organization, when you touch this piece of data, I want to make sure somebody inspected the code, and then the tool can actually give you some ideas. Yes. In our current implementation, no. Okay, but there's no reason why it shouldn't. You could save this along with the metadata, so when you open up, in our current implementation, as long as your workspace is alive, yes. But if you kill the app, you kill the workspace, we have this experimental code. We haven't gotten to the point of sort of making that persistent. Yeah. Okay, but there are a lot of UI issues, obviously. Okay, but this is the idea. Just this is the proposition. All right. So those are the just give you a sort of a very quick taste of what this interactive static analysis looks like. Let's go back to the presentation. Okay. Okay. All right. So again, to rehash, it is interactive data flow analysis is policy driven. Take advantage of essentially popular data flow analysis algorithms. We want to remind and assist developers fix each taint source through automatic validation and code refactoring, and instantly reanalyze the code. With control flow analysis, we identify critical sensitive operational code. And this is the part what I mean by leveraging application context and developer knowledge. So developer, as they are writing code, they say, okay, where did you do it? We believe that is the hypothesis is that's the time they're most familiar with the application context and knowledge. They could provide that information. And what I'll show you is how this kind of information can actually be used to do additional static analysis, things that you couldn't do in typical static analysis tools today. So, give you an idea of what sort of analysis you could do with this additional information that you couldn't easily do with current static analysis tool. So imagine this example. I'll give you a concrete code example later on. So you have some kind of web entry, right? And then it goes to some database access. And then you ask the developer, say, where is your access control check, say, for example, or CSRF protection for that particular update. And then this squiggly sign on the side is where the annotation is. And with that information, we can run static analysis by looking at all possible paths from all possible web entry to that particular database operation. And if we find there is a path along which there is no annotation, then that is a possible point for bypassing of authentic check, right, for access control. So we actually have found those kinds of vulnerabilities in real life code, and I'll show you an example of that. Now that's the kind of analysis that you couldn't really do easily with current static analysis tool, because the transfer of knowledge between your developers and your security code auditors sort of to write rules to do that is just so complex, it's just not going to happen. And so now I'm going to talk to you a little bit about evaluation. Okay, this is great. So, we're in research world, we're not in sort of product. So we have to say, how well that works. So we did an in-depth analysis of an open source project, Apache Rolla, which has about 65,000 lines of Java code, and it's quite widely used. So if you do, Google search powered by Rolla, probably over 1 million sites pop up, and it's actually actively maintained. So this is a reasonably well-maintained open source project. So what we did is first we look at evaluation of interactive data flow analysis. We take the Apache Rolla and we benchmark it against Fortify SCA. So we have John Melton, some of you may know him. He's here at the conference. He's the lead for the App Sensor project, and he happens to be a former student of mine. So I say, John, hey, I know you do a lot of static analysis. Why don't you do a benchmark for us? So he spent 2 days, did a professional job of doing static analysis on Roller. Right? So what he would have done for a commercial job. And then what we did was we ran this against Aside and compare our results against his results. We're using that as Oracle. So what we found was that Aside found, we're only looking for, Aside is only looking for taint source propagation kinds of problems. So 92% of the problems he found, Aside also found, right? And there are 2 issues that are not detected by Aside, but mostly those are JSP issues. We haven't really implemented JSP detection in our Aside yet. There's no reason why we couldn't. It just, it's a research prototype. There are some struts, structures that again, we have not implemented. So the ones that's not covered are the ones that we could easily extend our prototype to deal with. We also found some more things that Fortify didn't recognize as problems, but we found that they were problems. So these are problems, basically falling into 2 categories. One category is you've read untrusted data, but you sort of didn't do anything with it. So Fortify says, since it doesn't do anything, none of the rules trigger, so I'm not going to worry about it. Whereas we take the approach that says, if you touch untrusted data, we ask you to validate it, right? Now, the philosophy there is eventually, somehow, this data may get used through extension, so it's better to sort of validate it at the beginning. So those fall into these categories. There are some false positive as well. So an example of false positive is, somebody is reading it in a binary value, and it can only be interpreted as true and false. So that's very application specific, and Aside wouldn't be able to tell that. So there are some of those kinds of things. And out of the 118, we recognize, we classify 24 as being of that type. So those are the false positives. And we also evaluated interactive control flow analysis. So what again we did is, again, remember, interactive control flow analysis is about annotation. So we ran Aside against Roller. By the way, both this version is implemented by a former student of mine. She just defended her PhD dissertation. So we sort of took her code, we ran it against Aside, and so we simulated what the developer would have to go through if they were writing the code using Aside. And we were specifically looking for CSRF protection. So whenever the Roller changes its data, its state, adds, for example, add a blog entry, changes its state, we ask, where is the CSRF protection mechanism, okay? And sure enough, we found 7 0 days. There were 7 vulnerabilities that started at least from Roller 3.1 to Roller 5.1, which is the current release, that, they've done numerous facelifts in frameworks and all these jazz and UI, but those CSRF protection codes just sort of sailed on. So we pen tested all the versions in the middle. They all have these problems. We reported to the Roller team, and they fixed it, and they credited us for finding those Roller days, so 0 days. So that's sort of, in our mind, is at least preliminary proof that if you had something like that, hey, this is basically not rocket science, right? It's just when you're writing code, the tool says, hey, where is your CSRF protection? And we think that people know what to do, but they just forgot for whatever reason. So here is an example. This is actual code. So as you can see that this weblog save web entry, this is when Roller commits the web entry into the database. And at that point, we would have, as you see here with the red flag, we say, well, where's your CSRF protection? And the developer will look at this and says, okay, I checked for authentication, but I didn't check for CSRF. So hopefully, somebody would have thought about it and added to the tool, added the CSRF protection in. Of course, we cannot ensure whether they added it correctly or not, but at least they would have to think about it. All right, so that's the quick overview of evaluation, how effective it is. So we have some preliminary data against a open source project that seems like it should work, okay? We also thought about education as we started out with this presentation and say, well, universities don't teach secure coding. The reason is most faculty, like developers, never trained in secure coding, right? And we have security courses, right? We talk about, policies and, access control and all that, but we don't necessarily connect this with code, right? And so it's the same problem that we have in the industry. So how about using Aside as an education tool? So because most of our students go through the 4-year computer science program, will have to use Eclipse, Java to write their projects and stuff. So the hypothesis is, why don't we just throw this in there and see people can learn by using this tool. And we got a grant from National Science Foundation, so we built this evaluation exercise. So what we did was, when we do a demo, why don't we do a demo for the education version? Now, the education version is essentially the same version you saw, but what we did was we added a lot more explanations because we thought that these people would have never heard about secure programming. They, many of them have never heard about SQL injection. So when we throw warning at these people, we want to sort of explain to them what they do. So so this is our first attempt at doing that. So if you click on this thing, again, you see this. Along with the choices, we added the read more button, in which case we go online. And then we sort of explain what is input validation. You go on, and the type of attacks, and we also link in whatever appropriate material from OWASP website. So from there you can have jump-off points to OWASP. Right? So as an integration of that. So let's look at the dynamic SQL case. Right, so here's a dynamic SQL statement. You do read more. It says, don't do this, but we also tell people what they should do. So here's a page explaining what is SQL injection and how to do it right. In this case, use parameterized SQL statements. We even have sample code people can look at, and so on and so forth. All right? So this is the version we implemented, so it's designed to be used by students. And so what we did was to say, okay, we have to evaluate how effective that is, right? So let's go back to the thing. All right, so we did evaluation. We just before this conference, our paper got accepted, so I feel much more comfortable talking about it. So we recruited 20 graduate students who have no secure programming training at all, because they were just fresh master students or senior undergraduate students. And they were working on a web-based application project that uses, typical stuff, SQL, it's a Java-based web application. And we asked them to work in the lab on machines with Aside installed for 3 hours. We gave them a little bit incentive for them to do that. And we administered a set of questions, which are true-false questions, before they start the project. All right? So these are typical secure programming kinds of questions. And then we asked them to work 3 hours on their project. And then they can, by the way, this is all transparent. They can save their project as a WAR file and then go home and continue work on their own, on their laptops. So this is what we do. And then we also do a post 3-hour test. So in other words, we get a version of our test that very much similar, but it's a randomized, quite different set of questions, also true-false questions. We test them after they have used the tool for 3 hours. Now, what you would expect, being true-false questions, you get 50% chance of getting right? So indeed, before they use the tool, the average score is like 53%. So it's roughly about, random. But after, they got 10% increase. Okay, and we ran through standard statistical analysis tools, and it shows it's very statistically very significant. So the idea is, just after using 3 hours, they began to learn the concepts of input validation, of output encoding, and things like that. This is not with anybody teaching them. They're just by reading the material, going to OWASP, understanding those kinds of information. And another interesting thing is, remember the SQL statements, right? So for all the students, none of them use prepare statements. They all use Google, so we actually because we record their keystrokes using the screen capture functions. We see them actually go online, search, and they find, guess what they find? They find dynamic SQL statements, right? They cut and paste, they put stuff in there. None of them use prepared statements. But Aside warns them, say, don't do that, and then here's the stuff. Even though, for our ethical purposes, we have to go through ethical review boards for human subject studies, we could not give people extra credit for doing security right, because the course is not about security. We do not interfere with the way the course was taught. So getting the security right doesn't give students any extra points. But even in the context of that, 25% of the students voluntarily changed their dynamic SQL statements to prepared statements. Right? So that's kind of very heartening. I mean, so students really care. They see these things as they probably have heard about SQL injection, but they don't know what it is. So they understand it's a bad thing. What we see is for those 25% students, they would actually go on to Google search, find more about how to write prepared SQL statements right, and then sort of adapt it and put them in their code. So that's really interesting. So at least our preliminary results shows that if you have something like that, and imagine you can reinforce this throughout classrooms with professors, hopefully after 4 years, people see this thing repeatedly, that they'll understand a little bit about secure programming when they graduate. So that sort of concludes my second part of my talk. First part is sort of overview, just like a demo. Second part is evaluation, how well it works. Now I'm going to move to the third part of the talk, which is some of the research issues that we're working on. And this is not implemented. A lot of that stuff is still in the laboratory situation. Now, the current implementation of static analysis is, even though it's interactive from a user's perspective, but we're rebuilding the analysis every time somebody hits a key, right? Which is, for a classroom project, which is fine. The computers are fast enough, it's not a big problem. But for larger projects, that's obviously not going to work. So what we're doing on this, actually part of his PhD dissertation, is to look at multi-threaded incremental static analysis algorithm. So the idea is we take advantage of the Eclipse architecture. Actually, it's architected very nicely, that you have a sort of the JDT sort of base, and then you have a thread that deals with UI, because Eclipse wants to make sure that the user interaction gets highest priority. You do not want to freeze the user from doing anything else, right? So the plugin are relegated in separate threads. So what we want to do is we want to take advantage of this architecture by running our interactive data flow and control flow analysis in the background, utilizing multi-core processors. And then the idea is, go to the next slide. So as developers type in code and they change the AST, we want to be able to see, well, has the AST changed, and then build incremental changes into our control flow diagram and data flow diagrams, and then perform our analysis and get feedback to the developers. So we're working on this interactive version of the incremental version of the algorithm. I also want to talk a little bit about the path coverage algorithm, which I talked to you a little bit about, which is, once you have the analysis, how do you take advantage of this information and find additional vulnerabilities? So this is an algorithm, what we call the path coverage analysis. This is a particular analysis. Is again looking for invariants. We're assuming that the user is going to give us those, the developers are going to give us those invariants, and then our goal is to look at all possible paths throughout the execution of the program, see if all the paths are covered by Boolean checks. If they're not If they're not covered, then that signifies some kind of a bypass problems. So what we found, this was also reported last year when we were at OWASP last year, but it was not implemented. It was kind of a theory. So over this past summer, he actually implemented this algorithm. So we have a version of this algorithm implemented already. And again, we use Rolla as an example. So here's the actual piece of code in Rolla that had this vulnerability in it. And if you go on to there. Okay, so here's a piece of code where the one in pink, process sketch, right? So this is where you get the work done, right? And the reason it's done is because that's where the database gets updated, all right? And let's see, what is it? Okay, yeah, it was database that gets updated. And all your access control logic check are in what is the golden box in the handle. What is this called? The handle, get handler, all right? So we simulated what a side would have done with annotation. So we ask the user, say, hey, I look at your handle process get, which will update your database, right? Where is your access control check for this particular operation? And then you go through the code, and this is handle. There's a routine called authenticate, and then there is and you can see down there it calls verify user towards the end, right? And then so inside verify user you have the check of user ID and passwords, right? So from a developer perspective, annotation is fairly simple. I've coded the verify user. Here are two checks: check user ID, check password. Here's the access control. I've done my job, right? But if you go back to the code, because verify user is called inside this nested if statement, right? So if the conditions underlined in red fail, right, the user doesn't get verified, okay? And so that's an access bypass. So the path coverage algorithm will be able to find that because you've annotated user ID and password, and we found these paths that will bypass your access control. We will flag this as a vulnerability. And I suppose you can imagine that in revising and writing code, these things like that could happen. You take things, you put it in a loop, and pretty soon you lose track of which path you actually did the check. So we take this as sort of, again, some preliminary proof that bugs like that are out there, and that's really difficult to find with current static analysis tools. But again, by leveraging the knowledge of the developer, by sort of telling us a little bit about the semantics of the code, that we will be able to find those kinds of vulnerabilities. So again, this is the picture, high-level picture representation of this. So we did sort of our mental mapping of this against OWASP top 10. So okay, what sort of problems we can deal with in OWASP top 10? Obviously, injection attacks. We can deal with address this with interactive data flow analysis, cross-site scripting, some parts of undirected, unvalidated redirects and forwards, right? With control flow analysis, we can do broken authentication, insecure direct object reference. So when you reference an object, we can say, well, where's your access control check, annotation, CSRF, and then again, some parts of unvalidated redirects and forwards. So about 60% of the categories in top 10 can be in some fashion addressed by this interactive analysis. So again, a quick conclusion of what we have done is, again, the concept of interactive analysis by pushing it all the way to the developers in IDE. Again, two kinds of analysis: data flow analysis, which look at injection attacks, data validation issues, and control flow, which is dealing with invariants and policies. And we have evaluated with a reasonable open source project, and we sort of have a proof of concept, things that it might work. And we have tested out with students and see that it does have effects in terms of helping them retain and learn and retain information. And so here are some future work. Obviously, you know, we're working on interactive algorithms so that we work this incrementally. We've implemented path coverage. Now we have to put this together and we have to look at performance. Many people would ask you, so how fast it runs. No, I don't know. Okay, my hunch is it's going to be fast, but you know, but we have to have the code to prove that. So anyway, so I want to acknowledge the National Science Foundation for funding us this work, Fortify for giving us an education license so that we could do this kinds of stuff, and my student who is currently interning at Fortify for implementing the first version of the code. And most importantly, that all our papers and some of this code that we feel relatively stable are all our OWASP website, and it is our intention to, you know, eventually, as we find that things mature, well, this is the place where all the stuff will be made available to the community, and we love to get your feedback and down the road participation, contribution to code, etc. I'm sorry? Yeah, a version. I mean, the data flow part is available. We're getting ready to actually do a second release. The one that's currently out there is the older version. What you saw today will be out in the next couple weeks. We're doing a much more live study right now, so we have the code ready. So we'll ship it out in the next few weeks. We have really not looked at, you know, there's obviously a lot of usability issues, organization issues, and then there's also technology issues particularly with the way Eclipse handles things. Okay, so we're very open to that, but our goal, frankly, is right now to get the algorithm to work and get some results. And we haven't really gotten to that. I mean, theoretically, there shouldn't be any problems, right? I mean, it's just as we say, it's a matter of coding. But we haven't done that. I mean, whether that's better than the alternative, we don't know. I think we did look at find bugs. The difference is what we're trying to do is really interactive. I mean, find bugs is still very much like static analysis. You can run static analysis, for example, you can run Fortify inside an IDE, right, as a plugin. So you write your code, you push a button, you get results, and then you look at the results and you correlate to the code. And what we're trying to do is skip that step, run it continuously, and have the warnings be sort of presented right in the context of the code, as opposed to having the developer needs to look at the report. I mean, sort of my analogy is when I learned programming, you know, which was like, you know, many years ago, longer than I care to admit, that, you know, I used to have a deck of cards and throw it in, and somebody gave me printouts, and I look at the warnings and figure out which line. I mean, that's the mentality of static analysis today, essentially, is you read the reports and try to figure out. So we're trying to push it closer to the code. All right. Thank you. An open source OWASP project, so you can Google OWASP aside and you'll find the page. And so our design rationale is this is designed to be used by developers, not to security professionals. We want to have the developers be sort of recognize instead of recalling security problems. You see, instead of when I'm writing code thinking about what sort of problems I should prevent, we want the tool to tell the developers, hey, you want to think about that. All right, we want to by minimizing extra burden on developers, and then we also want to again leverage developers' knowledge in terms of customized security analysis. So with that, June is going to show the live demo of our system, both the interactive data flow analysis and the data flow static analysis, and I'll come back and talk to you a little bit more about some of the theory underlying design issue behind it. So So what he's going to do is going to show you an example in developers with vulnerability detection and prevention. We want to specifically leverage developers' knowledge about application context and logic to drive customized static analysis. Because a lot of times when you use static analysis, you're used by security professionals, and they don't really have the application context. So we're trying to use this tool to bridge the two, and we'll show you a couple of demos about that. And of course, the whole idea is to drive to fix vulnerabilities as early as possible, because we heard Gene Kim's talk that sometimes you don't get around fixing these vulnerabilities, even if you know they exist. So there's two kinds of interactive static analysis we have implemented. One is interactive data flow analysis, which everybody is familiar with, the typical kinds of taint propagation and injection attack sort of analysis for detecting injection analysis, injection vulnerabilities. We also are experimenting with what we call interactive.
All right. Welcome, ladies and gentlemen. Thank you for joining us. We'd like to give a thank you to our sponsors for this track, NT Objectives, that have sponsored this room and this track. We've got a great talk for you now on using interactive static analysis for early detection of software vulnerabilities. And we've got Bill Chu and Jun Zhu from University of North Carolina, Charlotte. They're going to speak to you.
Thank you very much. The story we're going to tell, is essentially doing interactive static analysis as developers type. So people are used to using IDEs like Eclipse. When you type in, make a syntax error, you get warned of results, of errors. And we want to do that for static analysis, finding software vulnerabilities. That's essentially what we're trying to do. I think Michael Howard's talk this lunchtime sort of sets the stage very well. Education is a huge issue. People are not trained. And even if people are trained, they often forget because you have pressures, deadlines, etc. So what we're trying to do is to fill that gap, to be very mindful, to keep it at the front of people's consciousness. So the basic observation is current static and dynamic analysis tools are reactive. You sort of do this after you have reached some checkpoint, so you're not fixing the bug as you produce them. You're sort of some distance away from that, and they're typically run by security professionals. So our approach is, as I mentioned earlier, is really push the envelope of interactivity along with the construction of the code while developers are writing code. Therefore, by mixed initiative, we mean it's developer-oriented, and we want to keep developers in the loop. So the advantage is, it's proactive, supportive development control flow analysis. The idea is sometimes you have security policies, invariants, things like access control policies, CSRF protection, etc. That you want to make sure that when you write code, you have satisfied those policies. And they're very difficult to detect with data flow analysis. They're really control flow problems. So we have some ideas on how to deal with that, and I'll share that with you. Now, I gave a version of this talk last year in Minneapolis at AppSecUSA. I will spend the next few minutes, just sort of give you a little bit of a rehash of what we did last year, because some of you may not have been there. But we have done a lot of new work since then, so we'll show you more results, and we'll also show you some of our current research things that we're working on right now. So with that, what I'm going to show next is our prototype demo of a project called ASI, which stands for Application Security in an ID Environment. And part of this is